In this math, we will find out the design bending moment for a W section, which is W14 by 74. And steel grade is safety grade still. And for the first criteria, you have a lateral support. So let's do the first problem. The thing is that if the section what you have is compact, let's say this one is compact, then the moment you will get is pretty simple. That would be just uh, let's say the moment will be Mn will be equals to Mp is equals to the grade of steel you are using and the plastic section modulus you will get from the AIC manual, and that would be the answer. And to use that, first of all, you have to prove that the designed or the given section is compact. If it is compact, then you can use this formula. So let's check its compactness. First of all, we'll check its compactness of flange. We'll find that out. Later, we'll find its compactness of wave, and we'll get these things from the AIC manual directly. I'm opening the manual, and here you can see that for the given section W1482, sorry, 1474, you have compaction criteria, and for that BF over 2TF, that is your compact or slenderness of flange, and that is your slenderness of wave. So one is 6.41, the other one is 25.4. We will compare this value with the plastic section modulus, sorry, slenderness. So for flange, BF over 2TF is given as 6.41, and for wave, we have been given that H over TW value is equals to 25.4, and the limit value, that is lambda or slenderness of flange at plastic point, is, there is a formula for that, that is 65 over root over Fy. In this case, the Fy value is 50. So 65 divided by root over 50 will generate a value of 9.19, and this value is greater than lambda Ef. So a flange is compact. Let's come to the wave part. The formula is 3.76 root over E over Fy. E value is 29,000 KSI and Fy is 50 KSI. If you put these values, you get a value of 90.55. And you can see that this value is way greater than lambda of wave. So the wave is also compact. If the section is compact, then the moment you will get will be just equals to the plastic moment, and the formula will be simply Fy, bro, I'm making videos, 5 minutes, Fy Zx, and for that the Fy value is 50 and Zx value is, for this math you will find it in the AIC manual. ZX value is right over here. Your ZX value for XX coordinate is 126. So you just multiply 50 with 126, and then you will get a value of 6,300 kip inch. If you convert it in terms of kip feet, you will get it 525 kip feet. And to get factored one, you just multiply mn with the factor, and the factor is zero point 0.9. Well, this is the math for the first part. We'll solve the later one. That is, if for the first part you have the lateral support, and for the second part you don't have any lateral support. If there is no lateral support, how you will do this? In this math, first of all, we'll find out that what is your L value. Your unbraced length is LB. We'll see that in which region your LB is there. If your LB is in this region, you can use simply the formula, that is Fy and Zx. If your LB value is within this range, then you have another formula. If your value is within starting from this range to uh, right hand value, then you will have another formula. So you have to find out where your values, LV values, are there. So let's do the second part. The LV value, unbraced length, that is given is 15 feet, and I will find out LP value. It is called the uh, length at plastic limit, and for that you have a formula, that is 1.76 multiplied by Ry root over E over Fy. If you go to the ASC manual, then you will find the value of R, and for Y axis you will find, and the value R is for Ry. So from there you can find out the value, that would be 1.76, and your RY value is 2.48. You will get it from there, and your E value is 29,000 KSI, and FY value is 50. Though it looks like 60, it is actually 50, and eventually the answer would be 105.1 inch. If you convert it to feet, it would be 8.76 feet, and this is actually less than LB value. So what I can say, that is, let's go there. Uh, LP value is that, which is 8.76 feet, and your value is more than that, so you are in this region right over there. So you have another formula for that. So we'll check another limit, that is, actually we have free region. So we'll first of all check if the value is within this region. Second, but in our case it is not actually. So we'll go to the second criteria, that is, if our value is within this region, and this region is called inelastic lateral torsional buckling zone. So we'll check that if our value is within this region. If within this region, then we'll use the formula for this region. So let's find out the another limit value, that is LR. The formula is pretty huge, a bulky formula, that is 1.95 RTS. What do you mean by RTS? That the value is given in AIC manual. RTS simply means radius of fillet, and then you multiply it with modulus of elasticity of steel, divide it with 0.7 Fy. This is just the formula, and then you multiply it with the root over value of J. See, here J is torsional constant. You find it to the manual, then you multiply it, divide it with by S and H naught. Here S is the section modulus, and H naught is, this is the distance of centroid, and then you multiply it with 1 plus root over 1 plus 6.76, and then you multiply it with 0.7 Fy S H naught over E and over JC squared. I'll show it in the ASA manual that these values are given there. You need not to convert in any unit. Here you can find out the J value. This one is CW. What do you mean by that? This is a warping constant, and this is sectional modulus. This is Ry. This is plastics section modulus, moment of inertia. You have everything right over here. All the things you need are there. So you just take these values from here and you just put these values right over here. So that would be 1.95. Your RTS value, you will get it from the ASC manual, 2.82. E value is 29,000.7. FY value is 50, and your Z value is 3.87, and your C value is actually your CV value, that is actually 1 given, and your S value is 112. You will get it from ASA manual, and H naught value is 13.4. 1 plus root over 1 plus 6.76, 0.7. Fy value is 50, S value is 112, and H naught value is 13.4, and your E value is 29,000 KSI, and J value is 3.87. Did I use it earlier? Yeah. J value is right over there, here. So that is 3.87, and C value is given. This is CB, that is 1. You just square that, and from the here you will get a value of LR, 371.2 inch, and if you convert it to feet, it will be 31 feet. So you can see that your LV value, which is 15 feet, is greater than LP value and less than LR value. So your uh, zone is this zone, which is this, and you will be your LP value was 8.76. So up to this point it was 8.76, and your LR value is 31 feet, and your LB value is 15 feet. So you would be somewhere right over here. So for this LB value right over here, we'll find we'll find this value. What is this value? So we'll find this value with an equation. The equation is uh, will be given in exams. The equation is a bit long, but not that much. The equation is Mn is equals to Cb. Cb is actually a factor. I won't go that much details. Just a factor that will be given. The factor is given for non-uniform moment variation. Anyway, the formula is Cb multiplied by Mp and another Mp subtracted by 0.7 Fy Sx, and then you just multiply it with Lb and subtracted by Lp, then you divide it by Lr minus Lp. That's the thing. So your Cv value is 1, your Mp value is, we got that in the first math, that is, sorry, this math, which is actually this 6300 keep inch. So we know that that is 6300 keep inch. Your that is the same thing, 0.750, and your S6 value you'll get it from the AIC manual, that is 112, and your LB value in this math is 15, and LP value is 8.76, and your LR value is 31, and LP value is 8.76. So from here, you'll get a value of 5,632 keep inch. If you convert it in terms of keep feet, you will get 469 keep feet. So this value is less than the previous one. If the section would reach plastic uh, point, then you would get a moment of 63,100 keep inch or 525 keep feet. So, but in this case, the value is 5632. It is around 400 less than that. And your factored moment is zero point 0.9 multiplied by 469. So the value would be 422 if it. So this is the answer. So for if your beam is braced, then thing is different. If your beam is not braced, there will happen torsional buckling, and for torsional buckling, the moment you're getting will be a reduced value. So that's the thing.